Hello, Finxters. How are you doing this week? I hope you're doing well in the summertime. I hope you have enough motivation to study for your machine learning or Python, despite still being able to enjoy the summertime. And today, I'd like to bring you another new tutorial. It is image classification using the TensorFlow Keras library. It's quite interesting for the dataset. It's Star Wars Lego images that is available on Kaggle, and we are going to take these Lego images of the Star Wars character. Actually, this dataset consists of a lot more Lego characters, not only from Star Wars, but let's say from Harry Potter, Jurassic World, Marvel, whatever. To keep things simple and friendly for beginners, we are going to just use the Star Wars images, and we are just going to use 5 out of the 10 classes. We are going to create a CNN model, convolutional neural networks, one model from scratch. So we are going to create a simple CNN model, and afterwards we are going to create another CNN model based on transfer learning, just to compare how these two would perform. But don't worry, I would like to invite you to code along. This notebook will be available in this GitHub link, which the link will be provided at the description below. So feel free to follow along. And classification Star Wars Lego images. Our task is to classify images of Star Wars figure Legos into 5 different categories using a convolutional neural network. Basically, the neural network will take images and then figure out which character that is. So the notebook for this tutorial is taken from this channel, Python Engineer, a channel that I follow a lot and learn a lot from. And this channel also provided its Jupyter notebook, and I modified it to be a little bit more suitable for beginners, for you to follow along and to understand it a little bit better. But yeah, let's start. This notebook, I do it on Google Colab because then we can utilize the GPU, but feel free to use your normal Jupyter notebook or Python script. I'm sure you know how to make the changes. If you have a GPU, I'm sure you know how to configure it. But here in this tutorial, I'm going to show you how to do it on Google Colab. So we have 3 main sections for this one. I think it's 3. Install and import modules, and then load dataset and preprocess data. And after the data is done, we are going to train and evaluate model. So this is the first 3 parts, and then an additional part is the transfer learning part, and then it's a comparison to see how different are these 2 concepts. So I might just explain briefly what is classification and so on. And if you are interested in learning more about TensorFlow Keras, about classification, regression, transfer learning, and so on, I would invite you to take a look at the Finxter's TensorFlow course that is built with beginners in mind. I think the first class is free for all, and the rest of the class is free for all Finxter Premium members. Okay, let's start. first and foremost, we are going to enable the GPU first. There are two methods, there are two ways to configure that. First, you can do from this edit tab, and at this notebook settings, you can see by default, before you configure it, it will be none. And now I've already configured it to GPU, okay? And then click save. The second method is go to this runtime tab and then change runtime type. And then as usual, change it to GPU and then click save. Here, if you want to check if GPU is present, you would do this. You would execute this line. I think I can move it up a little bit so that it's not confusing for you guys. Yeah, if you execute this line and if it returns you something like this, so device GPU 0 means that a GPU is being assigned for you. So if there's no GPU, you will see that it is an empty string. And then if you would like to, I will just move this up again. If you would like to check which GPU is assigned to you automatically by Google Colab, you can execute this line, basically saying comment NVIDIA SMI. You'll see the GPU that is assigned to you is Tesla T4, for example. Okay, after configuring GPU, let's install the necessary libraries. Here we are going to need NumPy for array slicing and manipulation, pandas for data frames, matplotlib for plotting, Seaborn, a more beautiful kind of plotting, and of course TensorFlow because we need to use the Keras. So just execute this line and move on to the next one. After you install it, it's time to import them. So import OS, Met. Those are the things you don't actually have to explicitly install them because they are all already available on Google Colab. Yeah. So we are going to use OS, Mets, Random, Shutil. I think those are more like to manipulate the dataset. So we'll see that later. We will use this raw dataset and then we will kind of change a little bit of its folder structure. And then we are going to use this for as well as this TensorFlow to carry out our project, our code project. Okay. Before we get to the model, first we need the data. So now we are going to load this dataset and then pre-process it. First of all, download the dataset from Kaggle and retain only the 5 folders of Star Wars. So go ahead to Kaggle. You might need an account to be able to download it. So go ahead and click on this download button. And after you download it, you might be able to download all of those things, all of those dataset at once. But what we want to do is you go to this Star Wars folder, the folder that you have downloaded. I think it has 15 categories, so 0001 to 0015, but we are going to just use the first 5. So make a copy of the dataset that you've just downloaded, and then delete everything and retain only this Star Wars folder that has only 5 folders inside. So you'll see, take a look. I hope you guys can see it. Yeah, the images look like this, and it's not a lot of images actually. But yeah, it's Lego photos with a Star Wars character. Four and 5. So are you guys able to remember which is which character, which folder is which character? But don't worry, we are going to everything is sorted out here. After you've downloaded the dataset and after you have removed everything and retained only the 5 folders of Star Wars, then we are going to upload it so that we can use it from Google Colab. So we are going to upload it to Google Drive. So just go ahead and sign in to any Google Drive of your choice. So I guess you guys know how to do it. So just go to Google Drive and then upload the dataset. And then the next step is to mount your Google Drive to be accessed by your Colab notebook. So means at first here, you will not see this slash. You see slash here is because I've already mounted my drive. So when you hover here, when you go to Google Colab, how to go to Google Colab? You just type Google Colab and then you'll be signed in with the Google account, that you use your browser on. So just create a new notebook or just upload this notebook on your Google Colab, and then you'll be bring to this kind of interface so that you can work with it. And after you've set up the GPU, then you mount the Google Drive. Actually, I think you have to mount, you have to set the runtime first and then mount the drive. So to mount the drive, you just click on this drive. So at first it says mount drive instead of unmount drive as shown here. So click on it and then it will mount your Google Drive. So the Google Drive is the one that is linked, that has the same Gmail address as you use this Google Colab. And then you will see this drive folder pop up. That is your entire Google Drive. And then you go to My Drive and then you locate the directory where you store your folder. I try not to expand it because then I have to post-process my video. So once you can see your data folder at your drive here, then we can proceed. And then this sample data actually is a Google Colab sample data. It provides you some example data set to begin with. So making your life easier if you want to practice some machine learning with these data sets. You can also, so instead of uploading your data to Google Drive and then you mount the drive and then you connect to it, another way is to directly upload your data set as a session storage. So session storage is the data is a one-time access. After you close this Google Colab, your data will be gone. And for the data that you uploaded, I think it will be available somewhere around here. But yeah, you can make the choice whether you want the data to be accessed only one time while you're using the notebook, or you would like to make it like a more like a permanent storage and then access that from your Google Drive. Okay. Now we want to check where is our current directory. So execute this line. You'll see that it's /content. So we will not have this is just to check which directory we are in so that we can refer that when we want to call the data. So here we want to rearrange the folders. I think I will explain it as we go along. Base directory, it is this content drive. So here is the drive, and then my drive, and then I store my data folder at Datasets and Star Wars. So I just put it this way. You might have a different data repository, so just modify accordingly. And these are the folder names that we see here. So 1, 2, 3, 4, 5, actually they are, the first folder is Yoda, second is Luke Skywalker, and so on, R2-D2, Mace Windu, and General Grievous. I apologize if I pronounce them wrongly. Okay. And next, we want to change the data folder from this kind of structure. One have different just images of one, like of Yoda, and so on. We want to change it to train dataset, test dataset, and validation dataset. And in each folder, so in train folder, it consists of these 5 different images. So folders of 5 folders of these 5 images. And then the same with validation dataset, and then the same with test dataset. But as we know that for training, validation, and testing, we will split the data proportion differently. So we will allocate the most proportion of the data to the train folder for training, and then we will then allocate the rest to the validation and test set. And that is why I wrote it here. Train proportion 0.6 means that 60% of however much data that is in the folder will go to the train set, and then 25% of the total number of images in the folder will go to the validation, and the rest. So the rest will go to the test set. I didn't explicitly say test proportion because we will just use 1 minus train minus validation. Here, the total train, total val, and total test is the variables that I created for the convenience of knowing how many images are in each of these folders when they are done segregating. Next, we are going to create the new folders. So you'll see that at first we only have these 5 folders. Now we want to create train folder, validation folder, and test folder, and we do it here. So if not os.path.isDir, so it will go, and this is a string format. So base dir, so this one, if Star Wars / train does not exist, then create these 3 data sets. Then create these 3 folders. Okay, so if inside this Star Wars folder, a folder called train does not exist, then we assume these 3 folders are not created yet. So for name in names, so names are the names that we created, the meaningful names that we created for these 5 classes of images instead of 0001, 0002. So for name in names, os make dirs, base dir train name. So at first it will create train folder. So it will create the train folder, and inside the train folder it will create Yoda, Luke Skywalker, and R2-D2. The same with validation. It will create a validation folder, and inside the folder it will create another folder called Yoda, Mace Windu, General Grievous. Okay, the same with tests. So you can imagine when this code is finished running, you will see 3 folders, and inside these 3 new folders you will see 5 folders. Does that make sense? Okay. So the next one, arrange numbers of images in each folder. What we are going to do is original folder 0001, 0002, and until 5. For folder index, folder in enumerate of original folders. runtime disconnected. I'll just reconnect again. Yeah, when you're using free version of Google Colab, it will run out of time after some time. So enumerate, when you use enumerate for looping, well, even if it is not for looping, enumerate always returns an index along with each element of whatever that you pass it in. So original folder, we know that this is the, original folder names. We want to loop it. So for each folder so after you loop it, you get folder index and folder. And then the current file that it is processing is os.listdir basedir plus folder. So it just means that the current file that I am processing is content drive my drive dataset Star Wars 0001. So which is exactly accessing the original folders. Folder name equals to names folder index. So we want to say, okay, because I would like to give it a new folder name. So I would say the current file that I am processing, the name is actually, for 0001, is Yoda. And then the number of images is, for name in files, name is the number of images in there. So for the number of images here, we say that for name in files, so this file, let's say it is the 0001 file. So for every element in this file, so let's say you can say for image in file, then you can collect every folder name in the file in the list. And after the list, because it's going to collect for the name for whatever number of items in the folder, and then you do a length. From here, you will know the number of images here. So this is the total number of images in a folder. And using this information, we pass it here, number of images, so total number of images times train proportion, which is 0.6. I want, out of this total number of images, I want 60% or 0.6 to go into the number of train. And then we do plus 0.5 is because maybe the train proportion of 60% is not it will end up in floating numbers. Let's say 9.5. And then we want to just round up the numbers. So we add plus 0.5 so that makes it 10. And 10 makes it integers. Okay, so this is just to make it round up if possible. And then this will become the number of training images for just the 001 folder, because it's going to loop through for all the folders. And then using the same thing, we want 0.25 to go to the validation folder. So number of images times validation proportion plus 0.5 and make it integers becomes the number of valid. Note that this is not moving yet. This is just counting how many images are there in each folder. Just from this folder itself, it's not the total number yet. Okay, and from this 0001 folder, out of this total images, minus number of training images, minus number of valid, is the number of test images. Okay, and so we are going to append this tree information to the total train, total val, and total test in order to get out the information of how many images really are there in the whole train dataset and validation dataset and test dataset. And then we print it out. We say folder folder name, which is this, Yoda. So you will see folder Yoda has this number of images in total, and then new line. This is the number of trained images, this is the number of validation images, and this is the number of test images. And this part is where the copy of images happen. This is the part where the images from 0001 to 0005 folders are moved into these new folders. Okay, so for index and file in enumerate files, so this files is from here, from the original folders. File name equals to the base directory plus folder plus file. Okay, so if this index is less than the number of train, so it means that it's going to load all the items in the folder and says if this index is within the number of train. So let's say if this folder has 10 images, and because train images is 0.6, so images at the position 1 up to position 6 will go to the train set, and then 7 and 8 will go to the validation set, and images 9 and 10 will go to the test set. So this is moving in order. So if index is less than number of train, then this util library will copy this file name from this file name to base dir train folder name. Okay, the same if index is less than number of train plus valid. So if number of train is 0.6 and number of train is 6 images and number of valid is 2, so that makes it 8. So because of this elif, so it will go through if. So images 1 to 6 will go through if. So images 7 and 8 will come here and then get copied to the validation folder. And else means the rest. So 9 and 10, if the folder has 10 images, will come here and then get copied to the test sets. And then we'll print the train folder has how many images in total, validation folder and test folder. It's the same. So the output is folder Yoda has 12 images in total. This is the original images, original folders. Train is 7, validation 3, and test 2. Means that out of 12 images, 7 goes to train, 3 goes to validation, and 2 goes to test. Okay, so folder Luke Skywalker has also 12 images, so it's going to be the same. So folder R2D2 has 12 images, the same. So folder Macy Windu has 13 images in total. So train 8, validation 3, test 2. And then General Grievous has 14 images in total, train 8, validation 4, and test 2. And then it says the train folder now has 37 images in total. So if you add up all the train, it will be 37. The val folder has 16 images in total, and the test folder has 10 images in total. Okay, I hope this makes sense. Now, we have a new folder structure that is just for our code project. We want to use, we want to do some kind of image pre-processing because the main thing that we want to do, the basic data pre-processing is to normalize the data. So we want to squash the range of these image data from 0 to 255. So from the range of 0 to 255 to the range of 0 to 1. We do this to imagine if you normalize the range of this image data, it's going to make your model easier to be converged, because your your machine learning model only have to try to optimize for the range of 0 to 1 instead of a huge range of 0 to 255. And what we do is, we are using the TensorFlow Keras functions, keras.preprocessing.image, the image data generator, and then the normalization is here. So we rescale 1.0 over 255. So after this rescale, your images will will just have a range between 0 to 1. And for training dataset, to add some variance to the input data when it is training, to avoid overfitting, we also add some more techniques to it. Let's say we rotate the images a little bit, we flip it horizontally, we make it shift in the weight and in the height, and then we zoom it a little bit, we shear it a little bit. Okay. But for valid and test dataset, we only normalize it, and we don't do any data preprocessing usually for validation and test dataset, because we want to make them as similar to the real world data as possible, to the original data as possible. Okay, the target size of the image is 256 times 256. Of course, it's a colored image, but this is the dimension that we feed into our model. And batch size of 4 means that out of this many training data set or validation data set, we only take 4 images at a time for the training. So train batches, we create this data generator, and then we use this data generator to do the flow from directory operation, which means that when this machine learning model is being trained, we don't load every single data on the memory, and because then this is a small data set that we are dealing with, so it might not be too big of a problem if we load everything on the memory. But imagine if you have like gigabytes and a lot of data, and you're loading that into the memory, and then for every rounds of training it needs these many parameters, so it's going to cause your memory to be exploding. So to avoid this problem, we use this .flow from directory function to say I only want to load 4 data at a time. So I will load as much as the batch is set. So here batch size is 4, so it means that I will only load 4 images at one time, train it, and then load another 4. So the directory is the training folder, target size, same target size, class mode sparse. Usually you can, usually people make it like categorical, but here we do not do one-hot encoding for the labels. And so in order to make the dimensions fit, we will say it is sparse. So which means that we want the output to be a single digit number. So to have the labels as an integer instead of one-hot encoding. Okay. So batch size is 4. Shuffle equals to true means that I want to shuffle the order of this training data set before it's being trained. Color mode, RGB, and classes are the folder names as category names. Very similar to validation batches and test batches, except that shuffle is equals to false. We don't usually shuffle validation and test dataset. and the folder directory is different. So validation for validation folder. And yeah, I think the rest is the same. For test dataset, put in the test folder and then make the shuffle to false. So after you execute this one, you will say the Keras library will say found 37 images belonging to 5 classes, 16 images belonging to 5 classes, and 10 images. So this is training dataset, validation dataset, and test dataset. So note that we are not training it yet. We are just defining the generator. We are just defining a function which will help to load the data, loop the data. And here we will have a peek at how the train batches look like. So train batch equals to train batch 0, means that we are just taking the first 4 photos of the train batch. Input shape is 4, 256, 256, and 3. So it means 4 image with this height and width dimension. And this is the RGB 3 color, the third channel. And then the target is 1044. So note that this is not one hot encoding, but it's just the integer as a category target, so as labels. So the same with validation batch and test batch. So far so good. Everything makes sense for now. So note that this target is, this is the second class, this is the first class, and this is the last class, because we only have 5 categories. Okay, done with this. Now let's have a look with how our data looks like. Not the real data, but the data that is loaded in the image generator. So we define this function called show, and then we say, okay, create a figure from matplotlib, and then for one in range 4, basically we create 4 subplots, and then we say x ticks, y ticks, and then grid to false, and then just show whatever images, the first 4 images that is there. Yeah, and then display the labels. So get the labels. If pred labels is not none, labels plus equals pred. Okay. This is the same function that is to be used later when the prediction is there. When there's prediction, it will be displayed. If there's not, then the if function will not go through to create another label. So display the labels as X label and then PLT show. So when we see show the train batch, which is the first 4 images, you see Skywalker, Yoda, Grievous as this kind of images. And note that because we did some transformation here for the train data set, so you see that this is a little bit rotated, this is a little bit distorted, and so on. This is a little bit crop out, like a little bit zoom in, and so on. But for the validation batch, it all looks kind of normal. And same with the test set. So it's not distorted or rotated or something like in the train images. Okay. Now you will understand that data scientists spend 70% of their time just fiddling with the training data set. Not training data set, just fiddling with data preprocessing. And then after all this time that we are looking at how to preprocess data, how to restructure the folders, now finally we come to training the data with the model, with a machine learning model. So here we create a CNN model architecture. First we define a sequential as model, and then we add that like a Lego. Not intended. Model.add. Add this first layer is a convolutional 2D layer. Number of units 32. 3 times 3 of the convolution pixels, so to say. So 3 width and 3 height. And move one step at a time as straight as 1. Padding valid means that the outcome, I want to pad the surrounding of the images so that the outcome will be the same shape as the input shape. So input shape is this, and then activation value. The second layer is a max pooling layer of units 2, 2. So the outcome of here will make the input shape to be half a size smaller. Next, another 2D convolution layer, but this time it's of unit 64. And then max pool, so decrease the size of the features into half a size smaller again. So 1, 2, 3, 4. Four layers, and then comes to flatten. This flatten operation is required when you are dealing with images, because you need to find a connection between these 2D images with 1D labels. So you flatten is to stretch the 2D images or features into 1D, so to say. And then fully connected layers.dense with 64 units, same activation value, and then output layer of 5 units. So usually output layer, you have to define the number of categories, and in this case 5. So for one-hot encoding, if your data is one-hot encoded, then you might need a different definition here. So usually there's this softmax activation, but we are not applying it here. So if you want to look at how your model architecture looks like, so just execute with .summary on your model. So you will see how many layers are there and how many params, total parameter to train for. So for this simple architecture, you have 15 million, is that correct? Yeah, 15 million parameters to train for. So after you define your model architecture, now we have to compile it, means that we add some more configurations to it. Loss function is to check how accurate is between the real data and the predicted data. In this case, we choose sparse categorical cross entropy, and we say from logits equals to true, means that we feed it integers and then it will do its job. And then optimizers is what we choose is Adam. So optimizers basically determines what is the strategy that the machine learning model to use towards gradient descent, to use towards making its prediction more accurate. And with the learning rate 0.001. And metrics is accuracy. So we are just trying to make things easy here. And then compile the model. Optimizer is this one, loss and metrics. Just fit into all these required configurations. Train the model with callbacks function. Now it comes to training part. Epochs equals to 30 means that for the same set of training data, validation data, we are going to repeat the training, use up all this whatever images that is there, and then repeat for 30 times. But this one is interesting. I'll just explain the fit first, and then I'll come to this early stopping. So history is the variable that collects all this different information like loss, accuracy, collects all your training information here. So model.fit is the function that trains your data. And then for training, you have to fit it, like usually you fit it training data and validation data. But here we actually fit the generator, the training and validation generator, so that it loads the data sequentially by batch. So train batches, validation batches, callbacks, early stopping means that, let's say I put here epochs equals to 30, but I allow the training to stop before the epochs of 30 is reached. And my criteria is, so I use Keras.callbacks, early stopping, monitor val loss, patience is 5, verbose equals to 2. So I will monitor if the validation loss keep getting smaller and smaller. And if this validation loss does not get smaller for 5 epochs, then I stop it. Okay, it means that if my model has smaller and smaller loss, means that it is slowly converging, slowly getting more accurate. But it has, when it reaches a point where it stops improving, and then I observe it for 5 times. So if after 5 times it is not improving or the loss is not getting smaller, then I stop the whole training. And verbose equals to 2 is just a different level of information that you want to see. Okay, then you fit in number of epochs. So this will actually start to train the data. And after this model has stopped, the history will collect all this information, and model.save will just save the trained model as base tier and with the model name Lego model.h5. And so we said it's 30 epochs, but it stops at 23 epochs and says epoch 23 early stopping, because it stops improving at this point. So we will see for training part, the initial loss was 8.8, which is very high. And then it goes down to 1.6, 1.5, and then to 1.4, 1.3, 1.2. And when it stops, it's 1.2, around that, which is still very high. So loss is supposed to be getting smaller, and accuracy is supposed to getting higher because we want to make it more and more accurate. So it goes from 0.1 to 0.3, 4, 6, 6, and when it stops, it's 0.4. Okay. Validation loss, it goes from 1.6 down to 1.2. So accuracy goes from 0.1 to 0.5, 0.6, 0.68. Okay, so basically we see that 0.6 is okay, not bad. But yeah, we kind of see like a trend of overfitting, because the validation accuracy is 0.68. It's fair, it's good, but the validation loss is still very high. So there might be a tendency of this machine learning model to just say, okay, I just put everything into one category or whatnot. That makes the accuracy quite good, but the loss is not so good. Okay, note early stopping, overfitting. Okay, but yeah, it's kind of normal if you define your own machine learning model, plus we are working with such small data set. Yeah, it's quite prone to overfitting. Now we will plot the training and validation outcome. So basically we just take all this information and then we plot it out. So figure, define a figure of size 16 times 6 inches, I guess. And then have subplot of 1 row and 2 columns. And then plot the loss as train loss, plot the validation loss as valid loss. And then give a legend. So this is the left side, and then this is the right side plot. So we'll see that this training loss is getting smaller and smaller, and then the validation loss is small. Okay, it's good, but then it is still over 1 for the loss. Training accuracy goes up and then goes down, and then validation accuracy goes up and then goes down and goes up again. Okay, so not optimal, but still we want to just evaluate it. So model.evaluate, it means that you fit in the test batches, and then it will give you what is the predictions, what is the overall loss and accuracy of the test data. So loss is 1.28, accuracy is 0.6. Still not optimal, not so good. Now we make some predictions. We also predict with the test batches, model.predict test batches. And then because we didn't use softmax, so we use the softmax here just to get the labels out of it. So use predictions, softmax, and then argmax the prediction, you'll get the labels. So the labels that are predicted here is 1, 4, 1, 2. So you will see here when it shows the data, original answer is Yoda, predicted Skywalker. And then this one also, original label Yoda, and then predicted something else. This one is predicted correctly, but yeah, this one is not so. Okay, so out of 4 test images, only 1 is correct. Okay, this is done for the classification, like our self-defined CNN model. And now we are going to compare it with a transfer learning CNN model. So transfer learning is, if you would like additional information, please refer to the Finxter TensorFlow course. So transfer learning is we take a pre-trained model, so a model that is trained with a good data set like VGG16 or whatnot, and then we chop off its output layer, and then we add something else. We add our own output layer to it. Usually it performs better because it's being trained with much more data, and we just have to fine-tune the last layer, so it's less work and also might converge better. But we'll see for this one. First, we define the model using TF Keras applications VGG16, and then type model. When you define this, it will download this pre-trained model from this source. And then when you print the type of VGG model, it will show you it is a function of TensorFlow. And then if you want to see how does the original VGG model looks like, just type .summary bracket. You'll see that this is the whole architecture. Especially you see it is being trained with 1000 categories because it has 1000 as its output layer. Now we want to take it and define our own model, our own transfer learning model. So as usual, we say model equals to sequential. So just define the start of this model. For layer in VGG model.layers. So for all layers in a VGG model from 0 until the one before the last layer. So it means that we want all layers except the output layer. Model.add layer. So we add every layer of this VGG model except its last layer. We don't want its last layer. And for layer in model.layers, layer.trainable equals to false. Means that for all these layers that I just added from VGG model, I don't want them to be trainable. Means that I don't want to fine tune or change any configurations of that. So I set layer.trainable equals to false. And on top of that, I want to add my own output layer. So model.add layers.dense equals to 5. We have 5 categories. So when we display the summary of our model, we'll see that all this architecture is the same, except as last layer is 5. So we only have to train this part, because you see, non-trainable total params is 134 million, and trainable params is only 20,000. Okay, so non-trainable params are all the other ones that we set to false, not trainable. We define the same loss, optimizer, and metrics, and then compile the model. And then we use the data preprocessor of VGG16 itself. So it means that here, for image data generator, instead of saying I want to normalize this and then zoom this or rotate that, we just say preprocessing function is the one that is from VGG16. Okay, we do this for the same for train, valid, and test generator. The target size we change to 224 times 224 because this is the requirement of the VGG model. Batch size, we make it the same. Okay, so all of these train batches, validation batches, and test batches are the same as the last one. I think even this is the same. So early stopping epochs is still 30, and then history model.fit. Model.save, we save it with a different model name, just for clarity. Otherwise, everything is the same. Yeah, you will see that it's also early stopping at epoch number 9 already. But here you see the validation accuracy is much better. See 0.6, 0.8, 111, and then 0.9. So it's much better than 0.6 as in the last one. And validation loss is also goes from 0.6 to 1 to 0.09. So much better than the last one already. So when we plot it using the same method, you see that it converges to 0.0. It's not 0.1 anymore. So validation loss is somewhere here. Validation accuracy is much higher for both train and validation. Accuracy is much higher for both train and validation data sets. And when you evaluate it using the test data, you'll see that the loss is 0.45, which is quite high. Accuracy is 0.9. But nevertheless, it's still better than the previous models. And if you predict it, so use the first for predict the first the test data, and then show the test data, you will see that Yoda is the original and predicted Yoda. Yoda predicted Yoda. Luke Skywalker predicted Luke Skywalker. And then the last one is false. So 3 out of 4 is correct, 1 is false. Instead of the previous one, only 1 is correct and 3 was false. And the color code here might be because of the preprocess input. So yeah, I think a better practice is to not preprocess validation and test data. But yeah, for illustration purposes, this is what we do. Okay, I hope this is a fruitful walkthrough of a code project for you. I hope you have learned something and maybe inspired from this code tutorial to maybe download your own dataset and start working on it. It would be a nice portfolio for yourself. As usual, have fun learning. Thank you and see you again. Goodbye.